Sure. So let me get started. Yeah. So again, Anna, thanks a lot for the invitation. So I know you guys has been organizing this topic on biometrics for quite some years. I think this is a quite important topic. So today I'd like to share some of our work as well as our view in terms of how we think, trustworthy biometrics, especially trustworthy face recognition, could be carried out into the future research. And the work I'm going to present today is a joint work with many people, and including Professor Anil Jain, as well as my students and postdocs at the Michigan State. All right. So let me get started. So we all know that we are at the stage of booming of artificial intelligence, right? So AI has been, being applied into many industry applications, right? Healthcare, transportation, and so on and so forth. And there's also a lot of attention on artificial intelligence, right? Both from industry as well from academic communities. Okay. And among many AI applications, one thing we are fairly interested in, of course, is biometrics. And this also is an area very active because of the impact of AI. And we all know biometrics has to do with identify individuals, right? We want to recognize individuals based on the behavior as well as biological characteristics. And typically when we talk about biometrics, we talk about, three major modalities: face, fingerprint, as well as iris. Among them, and many of those biometrics modality has already demonstrated a lot of applications, right? In when you go to airport, when you want to go to a park, Disney park, when you want to go to banks, so on and so forth. And biometrics, like different modality, has been used in so many different applications. So among them, what I want to focus today is one of the modalities, faces. We want to focus on face because this is the one of the modality I think gets most attention, sometimes positive, sometimes negative, among many biometric modalities, right? Because it has the ability of recognizing people sometimes when people are even not aware of it, trying to recognize people. Yeah. And the face recognition has been used in many different applications, such as mobile and transportation, as well as law enforcement, finding wanted people, finding suspects, right? So while facial recognition as well as biometrics are popular, there's actually increasing societal concerns on the technology, right? For example, Dr. Aaron Ross, and his collaborator had an article on New York Times regarding how the fingerprint, fake fingerprint can actually be authenticated into many cell phones. You start with a single, fake fingerprint, you can actually get into or unlock a lot of cell phones, which definitely will be a concern. And similarly, there has also been increasing concern regarding the fairness of face recognition systems, right? So this gentleman, whose name is, Robert Williams, he was actually being wrongly taken into police department because his face was matching with surveillance videos. And later, I found out that this matching was wrong, was wrongly conducted because of face recognition results. So those kind of incidents bring a lot of discussion, a lot of emerging issues. And those emerging issues has to do with the fairness of the technology, right? Whether the recognition result is fair to different demographic groups. And it also bring issues such as interpretability, right? When the face recognition is saying that these two faces belong to the same person, can we provide some interpretation for the results, not just simply, a binary decision from the models, right? And there's also increasing privacy issues because many of the face recognition data was, grabbing from the web without the consent of the people on the web, right? And there's also security issues. Presentation attack is becoming popular because of the wide application of the face recognition systems. So how do we make the face recognition system to be more secure, to be preventing those kind of presentation attack to be used? So with all of those things, we think that the trustworthy biometrics or trustworthy face recognition become a very important topic. right? In this topic, basically, if you look at the word trustworthy, according to the dictionary, the meaning of the trustworthy means that it's able to be relied on as honest as was truthful. Okay, so this can imply a number of things. For example, we want to have trustworthy biometric system to have sufficient security, meaning that we want to ensure we have truthful input by detecting spoofing or forgery biometric samples. So any spoofing or forgery sample should not be used for the recognition systems. So that's the security side. We want to ensure robustness, meaning that we want to have a truthful input by detecting any adversary samples, right? Which means that a digital sample which is used as input for the biometric system should not go through any modification. You should make sure that it has not been modified in any way before it is used for recognition purpose. And in the meantime, we also want to ensure fairness. With this time, we're talking about outputs, right? We want to have an unbiased output across different demographic groups, or across different racial groups, across different age groups, as well as genders. And there's also interpretability. We want to enhance the trust of the technology, of the recognition results, by providing interpretable outputs, right? And finally, there's also privacy issues. We want to develop privacy-preserved biometrics and for the society. And Dr. Jian actually recently wrote a survey paper on this trustworthy topic. So I provide the link in the bottom. So if you're interested, you can take a read of this paper. Yeah. So with that, today's talk is mostly trying to cover the multiple parts I was talking about in the previous slide. But due to time, I'm mostly going to cover security and robustness as well as interpretability. So let me start with part one, which I will be talking about security. And by the way, feel free to stop me if you have any questions. I like the talk to be a little bit more interactive, so feel free to ask questions. Yeah. Okay. So a general face recognition is working like this, right? You have a subject, you present a subject in front of camera, then you take a picture, and the picture being sent into a recognition systems, right? Eventually, when the match happens, the result of matching can trigger subsequent applications such as phone, setting up financial account, accessing to a gate, and so on and so forth, right? Now, when the presentation attack happens, it's usually when the suspect, showing a cell phone with a face on the cell phone, right? So this is a typical called a replay attack. So when this kind of face being presented to a camera will take a picture, it can just go ahead and send the picture into a recognition systems, they will still do the matching. So in this time, this will causing, wrong access to the subsequent applications. So this certainly is not ideal. So this want to be, prevented. So how do we prevent this? We want to have a face anti-spoofing system, basically serving as a filter in front of face recognition systems that can filter any input images to make sure that whether the input image is a live person or not, right? Only when the input is a live person, I will send that into a face recognition systems. Otherwise, for any of the attacks, I will try to block it. Do not send the face into a recognition systems. So that way, eventually, the subsequent application will be in a sort of much secured way. Yep. So face anti-spoofing, as we said, right, it's a technology that can distinguish the source of face, whether it's coming from a real human or coming from a spoofing material, basically. Okay, so over here, we're showing you a live demo, basically developed by my students, Yao Jie and Joe and a few others. So here, if you see the box being green, it means that it's alive. Every time you see a red, means it's a spoof. And we have been working on this for a few years under the government funding. So we have a fairly reliable demo systems to show how this kind of thing can work. As you can see, Bangjie was showing a paper attack. Now Amin is showing you a replay attack, I believe, right? So he's actually showing both his real face as well as spoof faces. You can see clearly the two window is with different color, one being green, one being red. And now Luang, he's also one of the former students. He's showing a 3D kind of head models. This will of course being considered as a spoof as well. Yeah. Okay, so even though we can have developed a lot of the anti-spoofing system using multiple sensors, but in general, from our previous work, we have been trying to working on monocular RGB-based solution. So we trying to use as little sensor as possible using a single RGB camera. That's what we want to do, okay? Because this is more desirable kind of application scenarios. And of course, as you can imagine, anytime you use face recognition, the anti-spoofing system will be necessary. You know, will be needed. So there's many kind of application scenario for this work. Okay, so let's talk about how do we do face anti-spoofing systems. So a typical approach will be trying to treat this as a binary classification, right? Because I can train a simple CNN, perform binary classification to classify any sample with either live or spoof, okay? So you can see that given this image, this would be live. And if I'm having the spoof samples, I will classify this as one being a spoof. So eventually it will become a quite straightforward binary classification problem. Okay, you can also use binary supervision for this kind of problem. However, this is problematic. You know, one of the big drawback is the overfitting. Okay, so why we have the overfitting issue? Well, the reason is that even though you provide the binary supervision to the data, but when the model trying to separate the positive versus negative, it's not necessarily using the spoof information for that kind of separation. For example, right, there might be bias due to the people wearing glasses, bias due to the color tone, due to the head pose, due to the genders. So all of those bias within the data can potentially contribute to the classification. So that's not what we want, right? Because eventually, if those cues are used in learning the models, then this model will not be generalizable to the testing data, right? Because in the testing data, you can have different distribution of the glasses, color tone, and head pose, and so on and so forth. So you really wish the model is using the spoof signal for doing the classification. That's the key. Okay, so this kind of overfitting is bad. So how do we prevent overfitting? Well, there has been quite some different ways to do this problem. One of them is called patch-based CNN. The idea is very simple. It's essentially, instead of training the model on the entire face, it actually trying to extract the local patch on the face and try to do a patch-based CNN to make a decision. Okay, so it's kind of I'm not using any global holistic face information, but only rely on the local texture, local information to make the decisions. So this will likely to force a model to see what are the high frequency difference between a real face patch versus a spoof face patch. Okay. Yeah, so it does show that this kind of patch-based method help to kind of mitigate overfittings. Second line of research is called auxiliary FAS, which means that we're not just doing a binary classification task, but we also ask the network to do auxiliary or side task, which can help with the face anti-spoofing. Now, typically, this kind of side task, including such as estimate a depth map or relative depth map, because the hypothesis is that many of the spoof examples, such as paper attack, such as replay attack, they are presented with a piece of paper or flatter plane, right? So that the relative depth of the face is quite flat. You don't see the nose being more closer to the camera. You don't see this kind of face-like depth. So this is important information for the network to be aware of and to learn it. So we are kind of providing these two different kind of depth map as a network to learn it. Okay, so that's one side task. Secondly is over time, we can provide the thing called RPPG signal, which means that when you observe a live face video sequence, you can potentially observe this kind of RPPG signal, which is indicative of the heart rate. However, if you observe a spoof samples, you may not be able to get this kind of RPG signals. So this is more like a temporal domain side task. So we published one work in CVPR 2018. Subsequently, there's a lot of work, doing similar ideas, trying to design different kind of side tasks to do face anti-spoofing. And the next challenge for anti-spoofing is actually there's a very diverse kind of spoof types. So here we're showing you different categories, such as 3D mask attack. But even on the 3D mask attack, you can see that we show you about the 5 different kind of 3D mask, right? Also, there's also makeup attacks. Makeup, we show you, there's obfuscation, impersonation, and cosmetic. There's different types of makeup attack. And similarly, there's also different types of partial attacks. So you can imagine, right, in the future, we will see more and more this kind of different spoof types, even newer ones showing up. So therefore, between training data versus testing data, it's very possible that in the testing data, you have some newer spoof types that you have never seen in your training process. Right? Suppose here I have, let's say in total, I have 13 different spoof types. What happened in the training, I only see 12 out of the 13. And in testing, I want to recognize this totally unseen, spoof types. How do I do that? So this is a very typical kind of problems. It has to do with generalization, basically, right? So there's many ways people have been trying to do it. One of the popular methods is called one class kind of classify. Basically, people trying to model the distribution of the real faces and try to forget about spoof attack, because spoof types are so many. It's very hard to model the unknown attacks, right? Why don't we just look at the real and try to find out the boundary of the real faces? Once the boundary can be found, then anything outside the boundary becomes a spoof, right? That's a simple idea. And but we found that this doesn't work well, for the real situation. So we designed a method called zero-shot learning and try to do this unknown attack detection. So this was published in CVPR 2019, one of the best paper finalist at CVPR 19. So the idea is very simple. We're trying to design a deep learning tree, deep tree learning for zero-shot face anti-spoofing. So you can see that we're essentially trying to design a tree structure that can classify or cluster, 13 or 12 different spoof types into different subgroups. Okay, based on how similar, among those different spoof types. The idea is that for any unknown spoof type, whenever in the testing, if I want to deal with these unknown ones, right? If I can find some of the known ones that's more similar to the unknown ones because of the spoofing material, because of lighting, and so on and so forth, right? Then any classifier based on the few similar ones has more chance to work well on this unknown testing samples. That's the basic idea. So this deep tree learning goes like this. So we have this convolutional residual learning called CRU, but this tree routing unit is very, very important. It's trying to take training samples and then put them into 2 different branch, left branch, right branch. And we do this recursively, right? Every time we take samples, put them into 2 different branch based upon some one-dimensional classification. I'll go to that later. So next level, I further trying to put them into different groups. Okay, eventually I will add a tree node, add a leaf node. At a leaf node, I will do a final binary classification to classify sample into real versus a spoof at a leaf node. But in all the intermediate nodes, all I do is trying to group the samples into either left or right, basically. So how do I do the grouping? Well, the basic idea is that I'm doing a PCA based on the feature representation, right? The PCA will find me the major axis, which the data has the largest variance within that dimensions. And on that dimension, then I try to find a threshold that can separate the data into 2 different groups. One go left, one go right. So I do this recursively for every TRU. So every TRU will learn the PCA, first principle dimension, then separate data into 2 different groups. Once I do this to the end, then in the final leaf node, I do the binary classification. So this way you can see that the feature space that was used to do this PCA was driven by the final binary classification. But in the process of doing so, we are actually proactively separate all the 12 different spoof type into 8 different leaf nodes. And so that during testing time, a testing sample will be routing through the leaf node that's most closer to the testing samples, and then do the classification in the leaf nodes. So that was the basic idea. Yeah. Okay, so the more recently, there's also additional works, and the more recent anti-spoofing work in the past 2 years, I provide some reference in the bottom, is more focusing on the we call the generative FAS. The idea is that the CNN is trying to train to generate some type of images to extract face sensitive features. It can be used for data augmentation. It can also be used for spoof tracing. So spoof trace is one of the thing we will be talk about. So what is a spoof trace? Why do we have to model that? Well, spoof trace is something fairly interesting. For example, let's say the first I show you 4 examples, as you can see here, right? Every example I show you 3 images. The first image is a spoof sample. The last one of the 3 is the spoof trace. The middle one is a difference between the spoof sample and the spoof trace. In other words, the middle one is also our estimated real sample given the spoof sample. In other words, we're trying to do a de-spoofing, right? Giving a spoof sample, we're trying to remove the spoof cues, remove the spoof signals, so that we can recover an image, recover a real image that's most closer to the input spoof sample. Okay, we call this as de-spoofing process. So you can see that this is more clearly, you can see the moral pattern, right? Once the moral pattern has been removed, this is more like a live face, right? The bottom left example is more like a makeup, right? We're trying to automatically remove the makeup so that the middle image is more like a live counterpart of the spoof samples. Similarly, on the right-hand side, we have paper glasses. We're trying to remove it, but you can see that this removal is not that trivial. You still see the edge kind of around the eye portion, right? This is kind of the transparent mask. So why do we want to do the modeling? So we actually provide a physicist-based modeling, try to describe how spoof faces are being generated. In other words, we talk about the spoofing process having 2 different processes. One is called additive processing. That is, a spoof sample is a live plus the spoof trace. So the addition of the live plus spoof trace will become the spoof. Secondly, the imprinting process, right? You have the live, you have the imprinting regions. So this imprinting region will say that in this region, I will generate a new pixels, imprint new pixels. And once I do that, I'll generate spoof samples. So we think that any spoof samples is a combination of these 2 different processes. One is additive, one is imprinting. So therefore, we have this equation, as you can see, right? Any spoof is coming from a corresponding live face plus some additive trace for certain areas. For certain areas that's outside the imprinting. However, for the imprinting areas, P equal to 1, let's say, right? It will coming from the imprinting trace. Okay, so given this equation, what we want to do is that given the spoof samples, can we inverse the process to estimate P, TA, I live, and as well as TP. So recover 4 parameters from the input parameter. Of course, this is a very much a ill-posed kind of inverse problem, but vision people like this kind of inverse problems. As long as you formulate a design network, having sufficient loss functions, even this kind of inverse problem can still be solved. Okay. So let's look at some results. So this shows you that giving some spoof samples on the top, you can see these are really different kind of spoof types, right? Giving some targeted live samples, we can actually, for every spoof source, we can estimate the trace, and then apply the trace to this target live samples. So this way we can synthesize a lot of new spoof data. So this is what you see in the bottom right. So only the first row, first column is kind of the real camera captured example. Everything else is a synthetic. Okay, so if you look at every column, right, you can see that those days synthetic data is quite interesting. It's basically kind of you learn the trace, then you apply the trace into this particular targeted live photos. So that way you can actually synthesize very realistic kind of spoof samples for those new subjects. So in our PAMI submission, we have shown that this kind of synthesized spoof sample is fairly high quality, and use those synthesized sample into the training process can actually improve the face anti-spoofing performance. And this is especially useful that because a lot of this kind of spoof sample is very hard to collect. It takes a lot of time and energy to collect. But if you can do this kind of synthesize, then you save a lot of efforts basically to do actual data collection. Yeah. Okay, so that's what I have for the anti-spoofing part. Let me switch the gear a little bit and try to talk about other face attacks, right? I talk about physical spoof attack, but we know there's also digital manipulation and attack, such as deepfake, as well as face morphing. There's also digital adversary attacks. So let me move to the digital manipulation. And this is face manipulation is right now become quite ubiquitous, right? And there's many concerns on this. People call this as deepfakes, right? There's even there's apps to do this kind of face manipulation in a digital way. And there's different manipulation type. For example, we call them as identity swap, and that's what you see on the left-hand side. We call this as expression swap, produce more new expressions. And there's also attribute manipulation, adding glasses, changing the color of the hair. There's also entire face synthesized, or the entire face image is completely synthesized, not starting from a real face, right? And finally, there's also, Photoshop of the face and the morphing from two face images, you produce a new face, sort of in between. Okay, so with all the different kind of manipulation type, one of the work we published in last year, actually CVPR 2020, was trying to say that can we design a single unified approach that can handle all the different manipulation types? So you can see that at that time, we were trying to deal with expression swap, identity swap, attribute manipulation, as well as interface synthesize. Our model not only provide a binary prediction in terms of real versus fake, but we're also trying to estimate the attention map, which basically trying to tell you that which pixel in the image has been modified, right? So you can see that for these three columns, so it's trying to indicate this area being modified. Okay, but for the interface synthesize, you can see that everything will be modified. So here, everything will be equal to 1. Okay. And to do that, we design an approach, which is not very fancy. If you ask me, the idea is fairly simple. We kind of provide a multiple way to supervise the learning. If sometimes we might have a supervised learning for the attention map, sometimes we have weekly supervised learning, and in the third case, we have totally unsupervised learning. So our model is trying to accommodate each one of the three cases, basically, whenever you want to learn this kind of model. And this shows you some of the results. You can see that every three columns belong to one case. The first three are all real. Next three is entire synthesize. This three is attribute manipulation. This is expression swap. This is the identity swap. And the column 3 are the ground truth manipulation mask. Row number 3 is the ground truth. The last row is the estimated attention map. You can see that this is still a pretty hard problem, actually. You can see that the estimated attention map is roughly similar to the ground truth, but it's still quite off. So I think there's still a lot of research need to be put to do this kind of manipulation localization precisely. Okay, so very recently, probably start from last year, we were interested in another problem we call kind of GAN, we call it GAN attribution or kind of reverse engineering of the GAN. So let me tell you what this work is about. So suppose, let's say at morning, right, 9 a.m., Los Angeles time receive an article, let's say, right? And the same day, Monday, 1 p.m., New York time receive article, and 3 p.m., Washington Post receive article. For all those news group, whenever they receive some articles, they want to, do an anti-deepfake algorithm detection to make sure that the photos or the pictures being submitted into news article are real photos, not deepfakes, right? So once they do that, it may find out that they are all kind of fake photos, all right? And then the next step following that will be called model attribution. Basically, they want to figure out that what kind of GAN model, which particular GAN model was used to generate that fake photo, for example. Okay, so this kind of model attribution typically is trained on some known generating models, right? We have GAN, we have VAE. There's so many different kind of GANs or VAEs can produce different fake data, right? So whenever you do this model attribution, you might find out that this is the unknown model because it doesn't belong to any one of the known generating model in the training process. So in that case, the question arises that, is this a coordinate misinformation attack? Meaning that all the three fake data coming from the same attacker, right? If this question can be answered, this is something quite important for the investigators, right? So we wish to answer this question basically. Did all the fake image coming from the same attacker? Okay, so this is not easy to answer, right? Based on the current, research that we have been doing, because right now for model attribution, we treat every model as different classes. For example, if I have 10 models, I call them as model 1, 2, 3, 4 until 10, right? Period. So there's no connection between different models. However, in reality, what we really want to do is trying to learn the embedding space that I can map those 10 different models into the embedding space, where I have a concept of distance, meaning some model may be more intrinsically more similar to the other models. They should be more close by, more near to each other in the embedding space. If that's possible, then the benefit is that given the three different unknown models, I can map them into this same embedding space. Now, if the embedding after mapping is quite similar to each other among the three, then maybe I can claim that, okay, even though these three models are unknown, right, but they are actually likely coming from the same attacker because of they are being similar in the embedding space. So that's kind of our motivation. Okay, now to actually make it work, we designed an architecture called model. We designed a task called model parsing. The idea is that any generative model, in our view, is coming from a different network architecture as well as different loss functions, right? That's how different GAN models, star GAN, DT GAN, BE GAN, right? Different GAN models, they're different because they're different architectures, they have different loss function to the training, right? So given the different network and the loss function, you can generate different GMs, generative models. And from those, you produce fake images, right? So we have this called fingerprint estimation network trying to estimate what is a fingerprint on each one of a fake photo, okay? And then given the fingerprint, we're trying to go ahead to do a reverse engineering to see that, can I start with the fingerprint, go through the parsing network to actually estimate or reverse engineering those network parameters, such as how many layers in the architecture, how many total parameters, where the upsampling is being used, right? As well as I want to estimate whether L1 loss has been used, ME loss, adversarial loss has been used. So these are the information I want to discover by looking at the fingerprint, okay? So we call this task as model parsing, basically reverse engineer how the generative model was produced by looking at the fingerprint, by looking at the photo in my hands, okay? And yeah, we designed a network to do this kind of reverse engineering. So we were able to show that, among different network architecture parameter, And, some of them are actually relatively easy to be estimated, such as, where the skip connection is being used, where the downsampling step is being used. But other parameters are harder to be estimated, right? Similar things for the continuous parameters, such as what is the number of fully connected layers, how many total parameters. These are relatively easy to be estimated, but others will be harder to be estimated, okay? And now this is how we visualize this so-called embedding space. We eventually learning taking 100 GMs, and we estimate their fingerprint. And this matrix showing the pairwise distance, pairwise similarity, cosine similarity between these 100 different GMs. Okay. Sorry, the font might be too small, but these are the names of the GMs. If you look at the detail, you see there's a few kind of unique fingerprint. There's a few groups. In these 4 groups, you can see that the diagonal elements are fairly bright. It means that these GM are fairly similar to each other. Okay. If you look at the name, you can see that they are basically different variation of the same GM. That's why no wonder, right? Eventually, the estimated fingerprint actually are very similar to each other. Okay, so we think this line of research can help us to eventually understand the relationship between different generative models, and eventually someone propose a new GM, let's say number 101, 102, or even number 200 different GMs, right? You can actually use this embedding space to tell him how different, how unique his GM is when compared to all the existing GMs. So it serves a way to kind of evaluate newly produced GM in the future. Yeah. So the idea we work on this problem actually is coming from our early CVPR paper in 2020, where we discovered that even for real photos, captured by different cell phones, such as iPhone, Samsung and Redmi, right? These different cell phones, they actually produce different fingerprints. Okay, so the second row are the estimated kind of noise pattern on different cell phone photos. And the last row is FFT, fast Fourier transform of the corresponding noise patterns. You can see that interestingly, the FFT is quite different among different cell phones, right? Okay, so we kind of borrow the similar idea to apply to the GM, because the generative model is kind of equivalent to the cell phone, because cell phone produce real images, but GM and generative models producing fake photos, right? So this work was actually quite widely reported by different medias. People seems like this idea. Okay, so now let me move to part 2. Okay, so I think timing might be one concern, right? I like to finish this in the next 10 minutes, so maybe I will skip through some of the contents. So next part.
Professor Liu, you can have until 20 past the hour, including some time for questions.
Yes, that's why I want to
Okay,
10 minutes, so I can leave 5
it's okay. Yeah, thank you.
Sure. Okay. So next, I'd like to talk about robustness. Basically, we want to detect adversary samples, right? And as we said, this is kind of one of the 3 way of attacking faces, which is digital adversary attack. Okay. So in this case, in this slide, I'm showing you one example of adversary attack. So suppose I have a real prop image. If I match with enrolled face, so this is a true match, as you can see. The face matching score is 0.72, right? In our system, we use ArcFace. Anything larger than 0.28 is considered as a true match, okay? So therefore, this will be considered a true match because 0.72 is larger than 0.28. However, if you have adversary face generator, you can actually take this real and produce adversary faces. Now, this adversary faces only when you match with the enrolled face, it only has a score of 0.24. That's bad because 0.24 is lower than 0.28. That's why it will be considered as a non-match, even though this face it looks quite similar to the input. Okay. So how do we deal with or defend this kind of adversary faces? Well, if you look at the previous work, there's different kind of scheme people do it. Either people trying to do direct detection, right? So this is more like very similar to anti-spoofing. I designed this detector as a filter, looking at every image. If it's adversary, I reject him. If it's real, I pass to face recognition module. Okay. The upside is that it's independent of the recognition, but it might have poor generalization abilities. Yeah. Secondary is purification, meaning that I also have a filter, but this filter will take any sample, no matter real or adversary, trying to make it clean, trying to purify it, right? And then the purified sample will be sent into AFS. Okay, the risk, of course, that if it's real data, you do some purification, you can potentially, the purify itself, it become adversary attack, right? So that's a potential issue. Finally, is a robust model, meaning that you don't have additional networks. You train this face recognition module to make it more robust to different adversary attacks. So this, the main downside is that typically the recognition performance will go down because of, it has to sacrifice some of the high frequency information, and as a result, you get a lower recognition performance. Okay, so what do we do in this problem? So we propose a method we call it the FaceGuard, which the idea is quite simple. And so we basically having a model to first of all trying to do a determination that whether it's a real or adversary. If it's adversary, we send into a purify, which is part of our model, and then generate a purified sample and then send into automatic face recognition. So you can see that in this case, it was 0.85. That's a good sample, but the adversary make it 0.29. That's very low. However, after our purify, this image have a new matching score of 0.78. So this will be considered as match. So yeah. And our model has been tried to detect the different adversary attack. So here are the different adversary attack method: FGSM, PGM, D4, and so on and so forth. So you can see that for all different adversary attack, we can have a fairly high detection accuracy. In the meantime, we're also trying to see what's the impact for the recognition. You can see that we design experiments on LFW. We're trying to say that once LFW data is poisoned, is adversely attacked, if you don't have any defense mechanism, you can have a very lower kind of recognition performance, as low as 34% true acceptance rate, right, at certain false alarm rate. However, if you see the previous method, you can see that they sometimes even can lower recognition performance. Sometimes they have some improved performance. But in general, our FaceGuard have a highest performance, starting from 34. We can increase all the way to 77. So on the right-hand side, we show you some visual examples. Okay, so in the interest of time, maybe I can skip this one. This is also one of the recent work. We're trying to see that how do we design a unified detector that can detect all three different kinds of attack, including adversary attack, digital manipulation, as well as spoofing. We think that in real world situation, you don't know what kind of attack you are facing, right? So therefore, a filter, if you have a filter in front of face recognition, you better let the filter or design the filter can detect all the possible attacks. So this is a kind of the objective. Yeah, let me skip the detail of this. Okay, so finally, I'll brief talk about the biasness as well as the interpretability. So biasness in face recognition is a big issue. So there has been many societal concerns. So we're definitely aware of this. We were trying to develop algorithms to be more unbiased. Make sure face recognition is more unbiased. So one of the early work we published, the first work we published on this topic was ECCV 2020. At that time, the main idea is that yes, face recognition can be biased to gender, such as gender classification, demographic, such as race classification, racial group classification. but the gender classification, racial group classification itself will be biased as well, right? When the racial classification itself is biased, it's really hard to determine that based on the bias, the racial groups, how do you know whether the face recognition is unbiased or not? So therefore, we want to design something that can simultaneously debiasing both face recognition as well as demographic classification, such as age classification, racial group classification, as well as gender classification. So we designed this in terms of a disentangle approach. You can see that giving a face, we estimate the 4 different latent code. Okay. So FG is for gender, A is for age, R is for racial group, ID is for face recognition. And then each one of them will do its own classification, for example, gender classification, age classification, and so on and so forth. But you can see we also have this dashed line. The dashed line essentially serves as adversary signal, which means that we want this FID have no ability to do the gender classification, no ability to do the age classification, as well as no ability to do the racial group classification. So in that way, we're kind of removing the gender, age, as well as the racial group information from the identity latent code. So that's the basic idea. Okay. We show that this does improving the so fairness. We reduce the biasness. However, because of some of the signals are relevant to each other, we actually avoid reducing the face recognition performance. That's not what we want. Okay, so therefore, in the next work, which is CVPR last year, we published a paper. We call it, a group adaptive classifier. So the goal of this work is that we want to improve the fairness, but in the meantime, we also want to improve the recognition performance. We don't want to sacrifice either one of the two. Okay, so the way we achieve this is trying to having a we call it the demographic adaptive classifier, basically, right? So you can see that here we have N module, A module. A module is basically the adaptive layers. So for adaptive layers, we have different filters. Each filter is for one demographic group. So if I have 4 different demographic groups, I will have 4 different filters in this adaptive layers. So that way, we eventually achieve both high recognition performance as well as lower biasness. And finally, I want to briefly touch the interpretability. So as we all know, typical face recognition encoding produce a vector, but this vector have no way to interpret it, right? It's just simply a 200-dimensional vector. You don't know what's the meaning of every single element in that vector, right? Typical, arc face, a lot of face recognition training scheme is like that. So this is not ideal. We want to do something like following. For example, given this two-face image, the previous work will generate a latent code, right? Eventually, computer cosine similarity, and then saying that they are the same person. But in our work, right, we want to say that, some of the feature vector is describing the eye portion of the face, some feature vector describing the nose, some feature vector describing the mouth in the final latent representation. And whenever that's the case, when we compute the similarity, we can actually tell people that, yes, they are the same person because their nose and mouth are similar. However, their eyes are not similar due to the occlusion in one of the pictures. So the eye, they are not similar. So that kind of information is what we can provide because of our latent code representation eventually is location dependent. So we will tie different elements of the latent representation to different facial areas. We do this through a loss function design. We design novel loss functions in the training process so that this kind of result can be achieved. Yeah. Okay, so let me have a quick conclusion. So we think that the trustworthy face recognition is a quite emerging topic, and they are important both technically as well as societally, right? We think the future of the biometric as well as face recognition technology will be depending on how well we can address the trustworthy issues. Yeah. And we also observe that there's many common issues among the different attack types, such as how well we can be robust to PIE, whether the defense system can be robust to low-level image processing, how do we deal with unseen types, right? Which happens for both physical attack as well as digital adversary, let's say. And the generalization ability, explainability, they're all common issues among different attack types. So therefore, sometimes we find it's better to tackle the problem jointly instead of only looking at the one silo, try to solve the problem. Yeah. Okay, that's what I have.